Well, in my presentation, I'm going to review the presentation from the face-to-face, and I will add the new things we have done. So the partners in wind energy are Barcelona Supercomputing Center, the French Institute of Petroleum and Renewable Energies, FAO, and possibly University of Stuttgart as a subcontractor. They will have a small task with us. So the codes. Alya is the code we developed at the Barcelona Supercomputing Physics. It's a finite element multiphysics code. It is the flagship code for wind energy, and it is also part of the Praise Benchmark suite, and it has been tested in most of European supercomputers. The second code is Walberla. This code is being developed by Ulrich Rude, and it's also a highly massively parallel code, and it needs to be adapted to wind energy simulations. For this, the people from EFP will provide the knowledge on wind energy, and they will interact with Ulrich and his group to try to get a code that is also suitable for wind energy. It's a very different numerical simulation. In our case, we are finite element. In their case, they are lattice Boltzmann. This means that actually the equations that they solve are actually different from the ones we solve. We solve the Navier-Stokes equation that is kind of the most common for fluid dynamics. They solve the Boltzmann equations. As a third code, the people from EFPN will use SOFA. SOFA is a code developed at the United States. It is based on OpenFOAM, that is a well-known open source code from the UK. And when it's developed at NRL, it has been adapted for the simulation of LES flows over terrain. Well, the people of EFPN normally use it, and we will do some comparisons between Alya and this code. Obviously, this code is not an Exascale code. In the US, they have a similar project to EoCoE. Actually, I believe it's quite bigger. And they are pushing for a new code that is called NALU that will replace SOFA, because they have realized that SOFA cannot be scaled to the exascale. So, well, motivation or brief explanation of wind energy. Wind energy involves lots of different scales, from the simulation of the wind over the whole planet. That is something we don't do. This then can be coupled with what is called mesoscale simulations. These are the kind of simulations Hendrik and the Meteo for Energy people do. These are much bigger scales. They simulate all of Germany or all of Europe, and their measures are much coarser than ours. They take into account different physics. They take into account the humidity and other things that we do not take into account. That are the mesoscale simulations. Then come microscale simulations. That is what we do mainly. This is simulating the flow over a piece of land. This is pure CFD, normal CFD. What the people in the mesoscale is not the typical CFD. This is what we do mostly. We simulate the flow over a piece of land, and we can take into account wind turbines. The wind turbines are taken into account as a porous media, as a force that opposes the fluid. There you can see several wind turbines, and then you can see the wakes that are formed. This is important for the people in the wind company, because, well, they want to place their wind turbines so that they get the less interference between one and the other, because this makes them lose a lot of energy. And finally, you have the blades. And there is a lot to be done also in CFD simulation. This is an area where I have not worked before. We have some people at BSc that have already worked in this. And it's one of the two tasks that we will also include in EoCoE II. We'll try to simulate a real wind turbine with the rotating blades. So again, a couple of pictures of what we do. Simulation of a flow over land, mainly the key parameters for the company are the velocity and the turbulence. Some other simulations. And well, so the specific tasks, as I said, are two tasks. The first one is development, verification, and validation for complex terrain. This is the micro-scale simulation. We just want to do CFD over a piece of land. In the case of EoCoE II, this will be large eddy simulations. In EoCoE I, they were RANS simulation. RANS is much cheaper. It gives you an average solution that is representative of the mean flow, but you do not simulate the transient. The wind is transient, you have gas and whatever. This is not simulated in RANS, but it is in LES. And the results for LES are typically much more accurate, especially when there is huge separation behind a mountain or whatever. It's much more accurate, but it is much more expensive, and well, we have Exascale, so it makes a lot of sense. What will we do on the physical sense? We will be working on improving wall modeling. That is the boundary condition close to the ground. Here you have to do special treatments, because if not, the LES becomes too costly, much more costly than what Exascale machines can handle. So you need to introduce some simplifications there. This is wall modeling. We'll also be working on the inflow boundary conditions, the turbulence that you put at the inflow. We plan to include thermal coupling. This is important because the wind is affected by the temperature, and how the wind behaves during the day and during the night is very different. We'll include Coriolis forces that are not always included in these kind of simulations. We'll include the canopy, that is forest, that also have an important effect on the flow. And actuator disk, this is the wind turbine as an actuator disk. Well, some benchmarking against SOFA will be performed. I mentioned SOFA is the code that EFPN uses. And we will test our model on real cases coming either from the literature, from the community, or also from Iberdrola, that is a company with whom we work. So a nice photograph of an LES simulation we have done over complex terrain. This is like an experimental case. It's a small hill with a cliff, and these are volume rendering of the velocity. Another example of something we have been doing lately, this is a very new case. It's Hornamossen. This is in Sweden, and well, the wind has been measured in like 10 different masts by a big group of people from different countries, and we want to simulate this. We have started simulating this. It's complex because the thermal coupling is important. Well, there are several difficulties, and probably we will have to couple this with the mesoscale model to get really good results, and this is something we are working on. We have started simulating this without Coriolis force. Then we have introduced Coriolis force. That also implies that you need to include thermal force. We have included the canopy. Here you have very good data for the canopy, or at least a lot of data for the canopy. We have been forced to use an implicit time discretization. That is not what we are using now, because the explicit time discretization coupled to the models that we use is still not working with Coriolis. We have used an unstructured grid with 216 million elements, and well, we run 3 hours of physical time in 6 days of computation. So these are some of the results. A cat, and well, you can see the complex terrain. There is a lake on that side. Well, this is the turbulent flow. We have used 2,000 meters of height, but we believe we will have to make the domain even a bit higher. This is, well, another result. These are the results for the cube vorticity. This allows the trained eye to see some kind of the structures that are formed. Well, as I was mentioning before, we have to work on the stabilization of the Coriolis force. We have observed that we still have problems. These are results for a flat piece of land where you can validate quite well. We had some oscillations. We have corrected that oscillations, but still we are not getting the correct profile with the explicit formulation. There might be a bug, or there might be something that needs to be changed in the numerical model. We don't know yet. Regarding wall modeling, we have been doing some very nice improvements. We have a new implementation that is very robust for complex geometries. And well, this is something that we are quite happy. We guess that we will be publishing this paper shortly. So, and this wall law is still not on the GPUs. We are working on the GPUs. Still, things are not perfect, but well, this is something that we have seen we need to introduce in the GPU version, and we will work on this shortly, we believe. We have to, as I said before, work on the Coriolis and continue improving LES simulations over complex terrain. The second task is the simulation of the full rotor, that is simulating a wind turbine with its rotating blades, the actual geometry of the blades. And well, the final objective would be to be able to do a whole wind farm with a lot of such wind turbines. This is a technology that is more interesting not for Iberdrola, but perhaps for companies such as Vestas that actually produce the wind turbines. It's important, for example, to reduce the amount of noise that is produced, or to get a higher life for the wind turbine. We have got a support letter from Vestas, and we hope that by the end of the project we could have something that could be of interest for them. We use a sliding mesh approach. That is, we have a mesh that is fixed to the blades and rotates, and this is in a small domain around the blades, and then the rest of the mesh is fixed. So there is a coupling. You have to have a coupling between the nodes that are rotating and the ones that are fixed. We expect to compare our code and get some knowledge from the University of Stuttgart that has been working on this subject for several years. We have collaborated with them in some other subjects, and well, we have an agreement with them to do a small collaboration in this sense, and we will subcontract them for this. And the people from EFPN will try to do an actuator line model. This is an intermediate step. You put a force where you have the position of the blades, but you do not actually have the real blade. This is called an actuator line model, and we will somehow compare with our simulations. This is an example. This is borrowed, these are results from the NALU code that I mentioned before. This is the Exascale code that they are developing in the US. There you have the blades, the mast, and the nacelle, and well, you can see the turbulent structures that are created. So this is a geometry result, a largely simulation of, well, in this case, a 5 megawatt wind turbine. And these are our first results that I am very proud or happy and lucky. It was, I would say, easier than what I expected. Everything worked quite well. So in this case, I just have the blades. I don't have the mast, but that is a small detail, or well, it's a further step. But we already have the rotating blades, and we can capture the structures well, and we do not see any perturbation where we have the interface between the sliding mesh and the fixed mesh. So this, I would say, is one of the nicest progresses we have done. Well, the mesh in this case is 50 million elements, but it will be bigger. Well, I'm so happy with this result. This is a cat. So you see the wake that is being formed. Obviously here the mesh is finer, so you see more detail, and the back you see less detail. Well, regarding full rotor, that is this kind of simulations, the next steps are to correct wall modeling for rotating subdomains. There we still have to do some small improvements. Improve the computational efficiency. We have to include the nacelle and the mast, that is the whole wind turbine. This is, I expect it not to be very difficult. We have to simulate more than one wind turbine and see the effect of the wake on one wind turbine on the next wind turbine. We need to add complex terrain to have a real flow over complex terrain. And then we want to start working on blade deformation. We have included a small part in EoCoE on solid mechanics that is trying to have a deformable blade and be able to do fluid structure interaction. We have a group within our department that works in solid mechanics, but they still have not started working on this. And well, then we have to start defining the collaboration with Stuttgart University. Regarding the things from EFPN, well, this is a slide that I already presented the last time, so these are the things that they will be doing. These are wind farm simulations using SOFA. You also have there a very nice rendering of something that is similar, but in this case I understand they do not include the blades, but they just include a force to generate this wake structure. And what else? Well, we were working on with SOFA, and on the other hand, they will be working on the Walberla code to try to use it for wind energy. Regarding the interaction with Work Package 2, Matthew mentioned yesterday that we have been working on the co-execution. That means using the CPU and the GPU at the same time. Typically what happens is that people use the GPU, that is much faster, and they leave the CPU do nothing, sleep there. We have found a possibility of also giving some job to the CPU, and then in total it goes like 15 or 20% faster. We are working on mesh partitioning with the space filling curve, and now we will be testing some other method from what I have been told. And well, the dynamic coupling between the rotating mesh and the fixed mesh, that, well, in this case it worked very well, but we have other cases where there are still some issues. Finally, testing towards the Exascale. This is something nice we have done very recently with the summer break. They stop Mare Nostrum every year, and so they gave us time to do some huge simulation. Well, in this case we run an airplane, but running a wind farm is not different from that. It's just creating a different mesh. When you want to simulate the rotating blades, well, then there is the coupling between the two blades, but well, this could be similar to running a whole wind farm. We have run here 2,000 million elements. This is still not what we have promised to the European community, but it's not that far away. We have promised 10 to the 10 or 10 to the 11 unknowns. So we are to 2 times 10 to the 9. We have an automatic division strategy where we divide each element into elements that are half the size. So in 3D, this means 8 times more elements. So if we apply the next division here, we would reach 10 to the 10. But we still have problems here. Well, at least some problems. Well, the first problem is that we needed all of the machine, nearly all of the machine to run this. We could have run it in a little bit less, but not much less. I understand that the smallest number of cores we need to simulate this is around 25,000 cores. The machine in Mare Nostrum 4 has in total 150,000 cores. So the smallest amount of cores we need is 1/6 of Mare Nostrum to run this simulation. It has been a real production run. This is not just a couple of time steps to see it works. We have run this for 24 hours in 2,000 nodes. This is nearly the full Mare Nostrum, 96,000 cores. We have also tested on the whole machine that are 3,000 nodes, that is nearly 150,000 cores. And here we have problems, and it's very difficult to know what these problems are. The problem was in the MPI reduce, and we don't know, but from what the people working with me have told me, they believe it's a fault of Mare Nostrum, not ours. What they have done is they have tried to use the 3,000 cores, but with the same amount of MPI processes that they ran the previous run, the one that worked, and it didn't work either. This gives us an idea that the problem is more with something in the software within Mare Nostrum or in the hardware, we don't know. And this is something where we need to have more time to do these kind of experiments. The people from Mare Nostrum should have more time to do these big experiments. And unfortunately, it seems it's only done once a year. So I think this could be a recommendation for this coordination of CoEs, that there should be time. We don't need too much time. We don't need to run for 24 hours, but we should be able to run for 1 or 2 hours in a whole machine, I don't know, every 2-3 months. It doesn't need all of the supercomputers, but if the supercomputers were stopped at different times, one could know and test, well, for 1 hour in the whole Mare Nostrum or SuperMOOC or whatever. So, well, we have also been interacting with the solvers group. We have interfaced the Italian group solver, PS Blast MLD2P4. We are starting to do some tests. Actually, they are starting to do the tests. We have finished interfacing with MAMS. This I did it some months ago. And here the testing will be done on our side. And this is something the solids people have to do because they are the ones that are going to use it. And well, they are quite busy now, but they will start shortly. With AGMG, we have already interfaced in the previous ECO. And I have obtained some excellent weak scalability results. So I will be running a huge case shortly. Well, I believe that I am more or less out of time. I don't know if anybody has checked, but well, the benefits I already mentioned this in the previous presentation. So, well, what do we want to do? We want to simulate the whole wind farm, including the full rotors. This is similar to this project in the United States. The idea is to drive innovation and improvements in wind turbine and wind plant design. There is a lot of knowledge that is not able to be obtained experimentally, and we want to complement the experimental data with numerical simulations to fill these gaps in what we know about the wind. And what will be the exploitation? So we hope that this can contribute to make wind energy cheaper. Nowadays, it costs more or less 5 cents per kilowatt hour, and it is expected that this could be reduced even to 2 cents per kilowatt hour, and this would make wind energy very, very competitive. On the other hand, another exploitation result could be to try to help reduce the noise produced by wind turbines. If we can understand better the flow, we can design the wind turbine blades better, so that they produce less noise. Well, obviously, Alya is a general purpose code, so the things that we develop here can also be used in other industries, and this, I believe, is a good point. Finally, and not least, we have an open postdoc position for somebody working on decoupling between the microscale models and the mesoscale models. So perhaps if there is somebody from Meteo here who knows somebody that is interested in working with us, well, we'll be more than happy to know about him. And well, thank you.